It is now my honor to introduce tonight's speaker. Dr. Luke Barnes is a postdoctoral researcher at the Sydney Institute for Astronomy. His university medal from the University of Sydney helped him earn a scholarship to complete a PhD at the University of Cambridge. He has published papers in the field of galaxy formation and on the fine-tuning of life, or fine-tuning of the universe for life. He has been invited to speak at the 2011 and 2015 St. Thomas Summer Seminars in Philosophy of Religion and Philosophical Theology, the University of California Summer School for the Philosophy of Cosmology, and most importantly, the prestigious Texas A&M University, as well as other numerous public lectures. His book with Geraint Lewis, A Fortunate Universe, Life in a Finely Tuned Cosmos, is available in hardback and ebook wherever books are sold. So if you would please join me in welcoming Dr. Luke Barnes.
Thank you. I'm going to start by doing something a little bit self-indulgent. I have a co-author as my excuse, and he wants to see evidence of what actually happened whilst I was all the way over here. So, okay, good. You do that first because I don't know what your face is going to look like by the end of this. I just feel I have some affinity with Texans, like Australians. There are a lot of people out there who expect us to say hello in a certain way. I could say, I'll say g'day and you all say howdy, but I think we're all better than that. So I'm just going to say hello and we'll move on with our talk. Can we get this front set of lights off? That would be quite good. Let me start off. I'm an astronomer, so let me start off with a gratuitous astronomical picture of a very beautiful galaxy, which you can enjoy for a second there. Our topic tonight is the fine-tuning of the universe for life. It is a topic in science which has a lot of people outside of science quite interested, so thank you very much for coming along tonight. So before we get on to what it all means, we need to do a bit of science. So what would really be convenient, because our topic tonight is about how the universe could have been, it would be great if I could just summarize for you how the universe is. So just spend a few minutes just teaching you all of astrophysics, right? So I will. That's what's coming up, all right? Everyone brace yourselves for this. I've done this for 10th graders. They all got it, so you will be fine. Someone less than 10th grade? Never mind. It'll be fine. You can get this too. Right. The reason we can do this is actually because the ideas, I mean, we can get complicated with equations. That's not going to happen tonight. But the ideas are quite simple. When we do physics, often we are looking for something which, despite all the balances of forces, all the pushes and pulls in the universe, is staying still. So I need one big word tonight, and that is the word equilibrium. That's all I need. That's when the forces balance. So, for example, here's a small hill, and there is a ball on the hill. There is the hill itself pushing upwards, gravity pushing downwards. There are two spots where the ball will stay there, which are here and down there. But if you put the ball at the top of the hill, a slight nudge will send it rolling off. So actually, the type of equilibrium that we're after is called a stable equilibrium, where you're at the bottom of a hill, where a bit of a nudge will not ruin the whole thing. It'll keep you where you are. So one of the things we can do in physics is have a look at the fundamental forces of nature, the fundamental pushes and pulls in the universe, and ask, how can I use those to make something stable, something that won't fall apart? So let me start by introducing those forces, and then we'll make some stuff out of them. There are four fundamental forces, as I said. I want to introduce two others. People at the back aren't going to be able to see the bottom of this slide. Don't worry, I'll explain all of that. Here we go. There are four fundamental forces, the four up the top here. You're all familiar with gravity, because you are all stuck to the floor. None of you are floating near the ceiling. That's gravity. You are not falling through the floor because the floor is held up by another set of forces due to electromagnetism. Basically, there are charged particles and there are magnetic forces, and for example, the ones inside atoms, which give us that kind of hardness, which means I can stand on the floor, is a example of electromagnetism. The strong and weak nuclear forces happen at the very centers of atoms. The strong force holds nuclei together, and in certain circumstances, the weak nuclear force will make them fall apart. That's all we need to know about those two. And, of course, there's not going to be an exam, so we can all chill out about that. I'll put 2 extra ones at the end there, which are conceptually different. They're ways in which the other forces work, but it'll help to keep them apart. Thermal pressure is just this. Things bounce around. So there is pressure of the air in this room against the windows, simply because air molecules are bouncing off the windows. If you put air in a balloon and then try to squash the balloon, you will be putting everything into a smaller volume, and so the particles will hit the side more often. So if you try to squash a balloon, it will fight back against you. That's all I really need you to know about thermal pressure. We can go back. Finally, there's something down there called quantum pressure. The very basic stuff of our universe, the atoms, when we get down to those very small scales, the rules change from what we're used to. And all I need you to know is that in certain circumstances, if it's true of the usual things we see around us, that they have thermal pressure, that they don't like being squashed, it's especially true of quantum things. There's an extra sort of quantum pressure there that says quantum things don't like being squashed. And there are the fundamental forces of nature, summarized in about 5 minutes. Okay, let's put these out for a test run. We're balancing them against each other. So we'll start by balancing electromagnetism with charged particles, which attract or repel, and quantum pressure. When you do this, you get atoms. If you put protons, positively charged things in a nucleus, and then put some electrons around the outside, the electromagnetism will hold it in, and quantum pressure will stop it from being completely squished. Voila, atoms. The wonderful thing about this is because it's a quantum system, these electrons go around in a specific orbit. When we put atoms close to each other, the electrons can go around a complicated orbit that takes them around the whole system. And that is how you bind things together with chemical bonds, in a very rough way. So there's our water molecule with H2 and O, and electrons in the outer shells going all the way around, holding it together. Our universe is particularly good at this, right? It's really worked out some stuff. That is DNA. Each blob there is an atom, and there are electrons weaving their way through that whole thing to hold it all together so that it can write the instructions for making a person. Okay? That is this sort of level of complexity we've got going on there at a chemical level. It's really rather great. But we want to talk about astrophysics because we're talking about the universe at large. So here we go. I'm an astrophysicist. Here is the one question that binds together an awful lot of astrophysics. What's fighting gravity? We want those forces to be in harmony with each other, in balance with each other. If you're out there in the universe, you've got great big massive things with a whole lot of gravity attached to them, so something must be fighting gravity. And all the different stuff out there in the universe we can understand by simply asking what is the thing that's fighting back. With that question, we can run through a whole heap of stuff we see out there in the universe and understand why it is there and why it is the way it is. So, for example, if nothing is fighting gravity, then we have a black hole. If this is where gravity wins and nothing can get out. I want to share this with you because it's pretty awesome. Here's what's going on. Why do we think that there are black holes out there in the universe? Well, there's a spot there that out in the night sky which represents the center of our galaxy. We're in a Milky Way galaxy, a whole heap of stars are going around. We can see the point which is in the center. And if we look with a radio telescope, there's something quite bright there in radio waves. What we can do with an optical telescope, one that sees as we see with our eyes, is look very closely at a very small region around that center for about 2 decades. Each one of those dots here is a star. They're not actually that big, that's just the blurriness of the telescope. We're going to start in 1995. Now, if you looked at a particularly just some random spot on the sky like this, you would see all the stars kind of drift one way or drift the other way. Maybe there's a little bit of, they're not quite all going in the same direction. But if we look at the very center of our galaxy, starting at 1995 and coming up till, you'll see it in the corner, up to about 2016, we see this. So this is a star. a billion ton nuclear fusion device doing a complete U-turn in about a month. Right? Whatever is there, A, clearly doesn't care that things are swinging around it because it hasn't moved an inch, and has the ability to make an entire star do a complete U-turn in about a month. Right? There is something there. Something big, about 1 million times the mass of the sun, put in a very, very small region, and basically there's no known form of force, no known form of matter that could hold itself up against that. We're pretty sure there's a black hole in there. Now that's not strictly speaking relevant to the talk today, it's just kind of awesome. Here we go, next one. What are we going to fight back against gravity with? Well, maybe just the ordinary hardness of matter, right? Atoms. Atoms will fight back against gravity. When we do that, we get planets. So the Earth is held up against the forces of gravity by its own matter, just the ordinary hardness of matter that we're all familiar with. Here are a few more of the planets in the solar system. Next step up, there's a limit to how strong that we can do this with atoms, and when atoms aren't strong enough, the next thing that kicks in is this quantum pressure. Things don't like being squished, and quantum things really don't like being squished. And I don't know why that happened. Sorry. We're back. Good. Maybe I'm lenient. Never mind. Okay. When we have that, we have what's called a brown dwarf. That's an artist's impression. The reason it's an artist's impression is because there are none particularly near us, and they don't shine very brightly. They don't glow or anything. They're not particularly hot. They're just kind of sitting there. So that's what we think they look like. Go a bit further up, something a bit bigger, and you'll need to balance it with thermal pressure. And now you've got yourself a star. When gravity is counteracted by thermal pressure, that's a star. To do that, obviously, there's a great big hunk of matter out there. Gravity is pretty strong. This thing's going to have to be pretty hot in order to do that. So it's going to glow. It's going to give out light. To counteract that, if you want to keep your star for a while, you're going to have to have a source of energy at the center to offset the stuff that's being lost. They will be done via the nuclear reactions at the center of a star. And that's, if you're feeling ambitious tonight, how to make a star. So, let me introduce some of the things in our night sky, how we've gone so far. This takes a bit of work, okay? There's the 4 smallest planets. There's Earth, which you may be familiar with. Australia down the bottom. Shrink that down to there, and then that's Jupiter. All right, ready? Shrink that down to there, and then there's the Sun and Sirius. Shrink Sirius down until it's quite small, about that big if you need to see it. And there's Aldebaran there. And let's do that again. Shrink that down to about that big again. There's Betelgeuse, and finally Canis Majoris, the largest star we know of. And that's the menagerie of stuff we see in the night sky. Those are stars. It might seem like that's a wide range of sizes, but actually it's this balance between the forces that tells us how big a star can be and can't be. If it's too small, then it will be supported not by thermal pressure, but by this quantum pressure, and so it won't shine. And if it's too big, actually these things are getting to the point where it won't be stable. It will pulsate and throw off some mass until it is stable. One of the things I love about stars is that they have to go through their lives and do such mundane things as fuel changes. They run out of fuel, so they need to sort of adapt themselves and get a bit hotter and burn something else. So here's what it looks like when a star undergoes a fuel change. There's a planetary nebula. It's misnamed, it's got nothing to do with planets. They look like this, or they look like that, or I could do this all night. Looks pretty good there. It looks pretty great here as well. What you really should do is get a nice dark room and a proper, high-resolution screen, and to get on the Hubble telescope website and put on some Beethoven and a nice scotch. Just chill out and have a look at some properly beautiful things in the universe. Okay, next up, how can we fight back against gravity? We can keep moving. Okay, so the way the Earth is not falling into the sun is because it keeps moving around at about 29 kilometers a second. Doesn't feel like it, does it? So if you keep moving, then gravity pulls your orbit into a circle rather than pulling you down into the sun, which is quite handy. We can do the same thing with we see here with this regular circular motion with random motions. So we get then what is called a globular cluster. So here's another pretty astronomical picture for you. Every dot on that screen is a star. There's a quote from Feynman at the bottom you might not be able to read. It says, "If one cannot see gravitation acting here, he has no soul." Okay, here's what we think is going on. Here's a simulation. So we put a whole heap of points in a computer and teach them to interact via gravity, and we kick it off, and it looks like this. So what happens is a star out here will feel the pull of all the other stars in the center, but when it gets to the center, it's moving quickly because it's fallen all the way in, and so it continues out the other side. And the whole swarm actually stays fairly stable. As a whole, the thing won't change very much, even while things are going in and out and on crazy orbits. Now, in that, even in the densest bit there, a star in the empty space around it is like a grain of sand in a football stadium. Actually, yours might be bigger than usual, maybe half of that stadium. So unfortunately, it would be awesome, but we don't see stars collide with each other. It's a bit of a shame, but there it is. That same dichotomy between orderly rotation and random motion we see writ large in galaxies. So where there is a galaxy which is supporting itself by orderly rotation, we see a disk galaxy. So here's the one that I started with. The galaxy goes around and keeps its nice stable form. If we looked at it from side on, we would see a thin disk. So here's a different galaxy, of course, viewed side on. There's another type of galaxy that does that random motion that I mentioned. These are called elliptical galaxies. Now, one of the reasons why you probably haven't seen a picture of one of these before is that they never really appear on astronomy calendars or in astronomy news because they aren't the prettiest things in the night sky. A particularly nice illustration of this that I like is that is called the Pinwheel Galaxy, and that is called the Needle Galaxy, and that is called NGC 3211. Because if you tried to name it, all elliptical galaxies would be like the smudge, the smear, the blob. There's just not much else to be said. So those are galaxies. Finally, the last bit is the universe as a whole is expanding. Whenever we see a galaxy out there in the universe, it is moving away from us, and moving away in such a way that a galaxy twice as far away moves twice as fast, and 3 times as far away moves 3 times as fast, and so on. So we understand that in terms of a uniform expansion of space. So if say the surface of the Earth started expanding once, everything at some time, everything would appear to be moving away from everything else. Okay, everything on the surface. If the Earth got twice as big, all other cities around here would be twice as far away. Okay? The universe is not an equilibrium system. Right? That is not a balance between two forces. It's changing as a function of time. Right? It's moving. The universe is not sitting still. That's how it's evading collapse. So, behold the Rosetta Stone. The answer to astrophysics all on one sheet of paper. If you're thinking of studying astrophysics, then don't worry about it. I've just done it all for you. Here we go. What's fighting gravity? We need to make things out there that are stable in the universe. If nothing fights gravity, you've got a black hole. For atoms, you get asteroids, quantum pressure, brown dwarfs, thermal pressure stars, and then the various types of either rotation or random motion give you the various types of galaxies, and the universe is expanding. All of that to say that we can understand the universe around us in terms of the basic laws that we observe in the universe. If we understand how gravity works and how electromagnetism works and all of these things, we can understand the structure of the universe that we see. When we do that, we end up with an equation. You can do, for example, you get out your equations and you balance thermal pressure with gravity, and you get an answer for roughly how big a star is. When you've done that, you have an equation. What is the average mass of a star? And some of the numbers in that equation are things like 2 and pi, things we're familiar with. And other ones are what are called the fundamental constants of nature. When we've boiled it down as far as we can go, we end up with these numbers. Things like how heavy is an electron, and how strong is gravity, and how strong is electromagnetism. When we've got there, that's the deepest level in our theories. So we might want to ask a question about why they have the values that they do. They represent the edge of discovery, and so a lot of physicists would like to know why they are what they are. Which suggests a different question, a related question. What if they were different? What if we took these numbers and changed them? What if we took the masses of the fundamental particles and the strengths of the forces that I've been talking about, pushes and pulls, and the numbers that characterize the cosmos as a whole, like how fast is it expanding, and what if we change them? Now, one of the reasons why we want to do this is because we don't know why they are what they are. For example, the strength of electromagnetism is a number, and Richard Feynman has said, a famous physicist, all good theoretical physicists put this number up on their wall and worry about it. Immediately, you would like to know where this number comes from. Nobody knows. It's one of the greatest mysteries of physics, a magic number that comes to us with no understanding. So, let's change the laws of nature. What happens if we take the equations we have and change those numbers? Here's a quick guide to this. Let's just give you a quick reminder about atoms. Remember the electrons going around the outside? The protons and neutrons in there. Actually, protons and neutrons are not fundamental. They are made of even smaller things called quarks. And you're either going to remember that when you get home tonight or not. Might have answered a trivia question for you there at some point in the future. Here's what we want to do. We want to change their masses. How heavy are the three basic bits, what's called the up quark, the down quark, and the electron? What we need to do is sort of represent the set of possibilities, the other values that these numbers could take on. So if we have three numbers, we can represent that in a three-dimensional thing. So here's our three-dimensional block of possibilities. If you pick a point in that block, you've chosen those three numbers in your universe. Our universe chose that one. There's the electron mass, down quark, and up quark. At the top, we've cut the block off at something called the Planck mass, which is where our theories basically run out of ideas for a very interesting reason. We don't know how to do what's called a quantum theory of gravity. We don't know how to put those two theories together, and the point where that matters is up the top here. So we don't know. Let's just cut off the possibilities there. There's a similar cutoff down the bottom. And this represents 10 to the power of 60. So to fit all that in, we're using what's called a logarithmic scale. If you need to switch off for about 30 seconds while I explain this, feel free. Instead of going 1, 2, 3, 4, 5, we go 1, 10, 100, 1,000. You put an extra 0 on each time, just to squish some more information in. All right, there's the menu. Would you like to order a universe? Pick a point in that block. Now, if I encourage anyone when they get home to go and make their own universes, let me help you out here by cutting off bits of the block that you'll want to avoid. So, for example, we want to cut off these two sides here. Don't make those universes, and here's why. Over here, remember we're starting to build stuff, okay? We take our quarks, we put them together, we make a particular type of particle. We take that particle and it won't stick to itself. And so we're done. It's a Lego set where you can put three things together and that's all you can do. The reason why that's a problem is the thing that you make has the chemistry of hydrogen, which is to say it undergoes one chemical reaction. Hydrogen plus hydrogen gives you a hydrogen molecule. So in this universe, if you have a chemistry exam, it goes like this. What is the element? Hydrogen. Question 2. What is the chemical reaction? Hydrogen plus hydrogen gives hydrogen molecule. End of exam. There is no one there to pass that exam, which is a real shame. Over this side, it's even worse. The only thing you can make there has the chemistry of helium. So the exam in that universe goes like this. What is the element? Helium. End of exam. Helium doesn't undergo any chemical reactions, right? Now, if you go online in our universe, there is something called the ChemSpider database, which lists the 15 million known chemical compounds in our universe. And if you're a masochist, you can work through all of those and then appreciate that there is one reaction here and no reactions over there. So avoid those. You'll also want to avoid stick in this region here, because otherwise either nuclei will eat electrons, and so all those lovely chemical orbits, that chemical bonds, they're all done, or protons and neutrons will fail to stick to each other. So we have in fact made two things, but there's no nuclei, and so once again you get the hydrogen exam. You want to stick in this bit here, just helping you out a little bit more by cutting off the universes in which anything big enough to burn as a star is unfortunately also big enough to blow itself apart, or in universes in which, because we've messed with the nuclear fuel of stars, nothing will light up. Anything as a cloud of matter collapses to try and make a star, it will be supported by quantum pressure before it lights up as a star. And so you only get brown dwarfs, so you don't get stars, you don't actually produce any of the other elements, you don't get light for life, so that you avoid those universes as well. Finally, stick in this little bit there, because inside, stars have the ability to make both carbon and oxygen. So you are a carbon-based life form, and you are enjoying the smorgasbord of oxygen that we put on for you. So carbon and oxygen are quite important. That's not just because we're made of those things. Carbon is by a long way the most versatile chemical element in terms of the chemical compounds it can produce. So that, if you need a picture of the idea of this talk, it's that one, okay? Here's our universe doing some really interesting stuff, like the whole of chemistry, for example. And very close by, and in almost all of the other things close by, in these other ways the universe could have been, are disasters for life. It's quite easy to just totally ruin the universe. By the way, remember this is a logarithmic scale? I had to distort it so we could all see what was going on. If I hadn't done that, in order to see this region here, I would need this screen to be about 10 light years tall. So, that if that helps you with the visual picture you have in your mind, then good. If you need a rather blunt visual metaphor, there's a razor's edge. If that helps anyone, good. Okay, you can take that on board. We can do the same thing with our universe as a whole. What I do for a living, and it's amazing that I get to do this for a living, is I study galaxy formation, how galaxies formed in our universe. One of the ways we do this is on a supercomputer. You start by dividing up a large region of the universe into bits that we can handle. A couple of billion would be nice. They represent a certain amount of mass in the universe. We tell them how to interact with each other via gravity, via the pull and push of gravity. We put in the thermal pressure that they push against each other. We teach them to glow when they are hot and form stars when they are dense. And we teach those stars to blow up when they get to the end of their lives if they are above a certain range. So you get supernovae feedback. We put all of that into an expanding universe, and then we put it on a computer, put it on about 5,000 computers, and hit play and wait for about a month and a half, and then we make a lovely, pretty movie out of it. The universe, we know, starts off very smooth. There aren't too many lumps and bumps in the stuff in the universe. If there are any lumps, though, there's more gravitational pull to those bits. And so gravity will make the rich richer. It'll take the densest, heaviest bits of the universe and make them even more heavy and dense. And so in this way, as the universe makes the densest bits of the universe, galaxies will form, and inside those will form stars, and stars will blow up, giving this kind of feedback you're seeing here. And the universe as a whole will form what's called the cosmic web, which you are seeing come together there. That is a very rough account of how we think the universe actually makes galaxies. Now, while that movie is playing out, what I've been doing is changing the rules. So I'm part of this collaboration called the Eagle Collaboration out of Durham University and Leiden in the Netherlands. Using the same computer code and the same initial conditions as a simulation like this, we can change the way the universe expands. What we discovered in 1998 was that the expansion of the universe is accelerating. Not only is a galaxy out there moving away from us, it's moving faster today than it was yesterday. This tells us that there is something in the universe called probably the cosmological constant. It might be something else, but that's the best idea we've had so far. There is a form of energy in the universe which causes its expansion to accelerate. We don't know why it is what it is. And when we use our best theory to guess what sort of possible range there could be, it's about 10 to the power of 120 larger than the actual value in our universe. Now, that's a number with 120 digits. What I've been looking at is what happens if you change that number a little bit, not by that amount. So, my simulations aren't quite as pretty as all of this, unfortunately, but let me quickly go through what we think we see. Here's one without the cosmological constant. That's the kind of hierarchy we see forming. What we can do next is, over this side, increase the cosmological constant by a factor of 100. Sorry, let me run ahead. What happens is, no, next one, sorry. There we go. As this one continues to form stuff, the cosmological constant makes this one accelerate earlier in its life, and it's now frozen. Everything in the universe is now too far away from everything else for gravity to start pulling stuff in. I can run that again. So while this one continues to form galaxies and stars, this one, if you haven't formed after the first fraction of the time there, then you won't form anything because everything is too far away from everything else in the universe. We can have a look at this a bit closer if we zoom in. So here's what's happening. Here's, over this side, two galaxies will form and then collide with each other. Over here, two galaxies will form and then miss their appointment. They've been carried away by the expansion due to the cosmological constant. And if we kick things up a notch, here's with 100 times the cosmological constant, all of this stuff, which is providing fuel for stars and planets and all that kind of thing, all the things we rely on is going on, and this side is totally frozen. Time is still going on, but gravity is not making anything. So that tells us that the cosmological constant is fine-tuned for life. With just 2 orders of magnitude there, I can make things shut down pretty quickly, and we've got 120 orders of magnitude, powers of 10, to work with. So what we can say with quite a bit of confidence is that if the cosmological constant was, say, 10 to the 10 times larger or 10 to the 20 times larger, the universe would stop making structure before it made any structure. Everything would be too far away from everything else before any galaxy had a chance to form. And so a very easy way to make a universe that's totally devoid of life is to have it totally devoid of any structure whatsoever. Pretty soon, in those sorts of universe, every proton is just going to be kind of alone in empty space, and that's all that will happen until for the rest of the history of the universe. Those are some examples of what is called the fine-tuning of the universe for life. When we take these numbers and change them, it's quite easy to ruin the universe. Now, if you want to see a whole lot more of these, Geraint Lewis and I wrote a book about all of them. There's some very entertaining ways to ruin the universe in there. I've given you a couple. If you need a few more ideas, if you're a aspiring supervillain of some sort, we've given you some great ideas there about how to totally ruin the universe. We have some copies, but unfortunately we weren't able to get the paperwork to sell them here. So if you want one, either Amazon or follow us to the car and steal one and then just send me 25. Never mind.
Talk about ruining the universe.
Yeah, ruining the universe. Yeah. So now's the time when I should probably tell you that Geraint is an atheist. We wrote the first 7 chapters of the book together, taking it in turns, and there is basically one footnote where we disagree with each other, which starts, at this point, our heroic authors got into a bit of a scuffle about ... I'll let you work out what was going on there. But the science here is I can't say uncontroversial, but fairly uncontroversial. What we're really doing here is summarizing what's been going on in the scientific literature, and it's the kind of thing where we agree about basically all of the science. And then in Chapter 8, things get interesting, because we disagree about what we should conclude from this. What Geraint thinks we should conclude is that our universe won the cosmic lottery. The reason why we got lucky for life is because there are lots of other universes out there. All their properties are changing at random. From universe to universe, not with time. And so in most of those universes, there's no one around to complain that they're not right for life. But every now and then, where a life form pops up, they'll see a universe which is just right. This is called the Multiverse, which has found its way into comic books. Infinite Crisis, the fight for the multiverse. There is very little mention in the scientific literature on the multiverse of Batman. I don't know why he gets a mention here. And Spider-Man. Where's Spider-Man? I don't know who that is down there. Never mind, we're getting off topic. Okay. Why would we think that the multiverse is a good idea? Well, some of the theories we have about the very early universe might suggest that this sort of a bubble-like structure is the overall structure of the universe. We find ourselves in an expanding bubble, but that will be one small part of a greater ensemble of bubbles. Now, that might sound pretty speculative, because it is, but this is cosmology. It's always going to be a bit speculative. We're trying to work out what the whole universe is doing. That's one reason why you might think to take a multiverse idea seriously. What I want to look at very quickly is one way in which this idea might be wrong, and provably wrong. Okay? Now, this talk's been pretty weird so far, so if you're with me, here we go. And if you're not, then just chill out for about 5 minutes. It's called Revenge of the Boltzmann Brains. Here's the idea. Okay? Yeah, you should stand up at the back if you want to see a picture of Fry from Futurama. Here's the idea. If you're a cosmologist and you're modeling the entire universe, whether you like it or not, whether you realize it or not, you are modeling a system that has you inside it. Okay? We can't pretend that we are sort of standing outside of our apparatus, just sort of looking at it. And so when you want to say, what would I expect to observe if my idea about the universe were right? We have to take account of the fact that the thing we are modeling includes observers. It's not just how likely is it that this thing would turn purple. It's if I want to know how likely is it that I would observe that a certain thing in the universe would be observed. The universe first has to make observers and then have them observe something, because you are modeling the system that you are in. One of the ways in which we can test the multiverse is to think, okay, let's think about taking a survey of all the observers in our multiverse. Let's get our clipboard out and go around to all these other universes, in our heads, of course, and simply ask a question. If we find someone there, we'll ask them something. Now, most of the universes, for the reasons I said, are going to be dead, right? They don't get the right bit of those plots I showed, so there's no one there to ask. But if you do find someone, ask them a question about their universe. How big is it, for example? How did you come to be as an observer? How did the universe make you? Because the story of these simulations I've been showing, and of cosmology, is the universe made us by a long process. But in certain multiverses, the easiest way to make an observer is not by making an entire universe that does a whole heap of things and making a whole lot of observers. It's easier just to make one. And not to have to bother with making stars and planets and all that nonsense. Just make that one universe pop out of the chaos. If your multiverse idea is doing that, then you've got a problem, because it predicts something. It predicts that a typical observer in that multiverse will not be like us. They'll be a single brain floating in space. It's the easiest way to make something which is thinking the things that I am thinking now. So that's a problem. It's a straightforward case of a theory making a prediction and getting it totally wrong. And so that theory goes out. So in spite of the fact that we might think that the multiverse is a totally speculative thing, there are ways for it to be totally wrong. The other reason why this topic of fine-tuning is interesting is that to a lot of people it suggests the existence of a fine-tuner. The way I like to think about this is to imagine some chess pieces standing on their chessboard trying to work out the rules of chess. So they do science. They make observations of the world around them and try to piece together what is going on. They find out it is a rule that bishops move diagonally, and if they keep watching even longer, they see rarer things like castling. They might reach a point where one of them works it all out and is able to write down the actual rules of chess. And then they would have this rather amazing moment of being able to just stare at the rules that govern their entire universe. They might notice something about those laws. They might wonder why those laws are not other ones. In particular, why aren't they playing checkers, for example? Why these particular laws? They might look at other possible ways that their laws might have been. For example, here's a favourite case of mine. Suppose that they had rules where, instead of saying that the knight can jump over other pieces, you say the bishop can jump over other pieces. That is a game that is very like chess in its rules, but is not very like chess in its strategy, because you can get checkmate after one move, which kind of ruins it, okay? The entire game becomes no more interesting than flipping a coin to see who goes first. If they noticed that every time they made a little change to their law, the laws of their universe, something like that happened, and the game they were playing suddenly became a lot more boring, they might think maybe these laws were laid down for the purpose of making a game that was interesting to play. They could not possibly get that sort of explanation from the laws themselves. The rules of chess will not tell you why you are playing chess. So we could imagine in the distant future, Einstein's great-great-great-great-great-great-granddaughter, Alberta, walks up to I don't know why Alberta is funny, but everyone laughs at that. I think it's funny too. It's awesome. Walks up to a blackboard at a meeting of really important physicists and writes down some equations on the board, and fundamental physics is over, right? We're done. It'd be like discovering the laws of chess, right? We just know the way that our universe works. And you might start to wonder why it is that these laws are the laws of our universe rather than some other laws. Now, if you ask that question and you want an answer, you will not get it from the chalkboard. Right? There is no mathematical equation that says, I'm the one that describes reality. There's no math that's so pushy that says that reality must conform to me. So if you want a reason for the laws that we see, you're going to have to look elsewhere, look deeper than ordinary scientific things. I think the idea behind the fine-tuning of the universe for life as an argument for the fine-tuner is, if we take these laws and think about all the other possibilities, which in this case is just every other mathematical equation there has ever been. Think about writing them down on one huge chalkboard and just keeping Alberta's little one in the middle there. Of all these possibilities, if we finish our explanations at the laws of nature, we'll never know why that one rather than all the others. And worse than that, it's not just that we'll never know, it's that there is no reason for it. If we get a tip-off, though, that the laws of nature are the way they are to achieve some good purpose, then we might go a step further to explaining why the universe is the way it is. So if you think that the universe was created by a good creator who would want to create beings that themselves have moral value, that can love and be loved, then you have a huge clue about which one of those possibilities is the actual one. Okay? That is a property of good explanations. My illustration of this that I particularly like is as follows. If you're familiar with the game Guess Who, the idea is you're trying to guess who the other person's person is, your opponent's person is, by asking questions about what they look like. Are they wearing glasses, for example? If you ask a question, the really good questions are the one where you get to flip down a whole heap of the answers, right? So, for example, if you ask, does your person have both a moustache and a beard, and the other person says yes, then it's Richard. Right? You can all imagine the game of the memory from my youth, where some game of Guess Who went catastrophically for me. That lets me that I remember that particular fact about Guess Who. You're all filling in details in your head. That's perfect. Good explanations take a whole heap of possibilities and flip down lots of them. They help us understand why it is the way it is rather than some other way. So I think when we get back to the ultimate laws of nature, if we know that only a very small proportion of those will allow something good to happen in the universe at all, then the idea that the universe is the product of a good creator does a lot of explanatory work for us. Now, obviously, Geraint disagrees. And if you want to see how that discussion plays out, then get on Amazon or follow me back to the car. This is called the Finetuning of the Universe for Life. And I've presented it to scientists and to philosophers, and if you present it to 10 people, you get 12 different answers about what the answer might be. So I'm very excited to see what I get here. So thank you very much for coming.
Okay, so the first question is, if it took the cumulative whole of human knowledge to develop our basic understanding of the universe, is it rational to believe that one being was simply endowed with it?
So, endowed with it's the wrong way to think about it, right? There's really a difference between two worldviews here, and you need to not mix them up. One's called naturalism, which basically says that physical stuff is the only stuff. The very short definition. Everything that exists is ultimately made out of this material stuff. So if you have something like a mind or knowledge, that needs to be made out of stuff. And if it learns something, it means you have to make it learn something. On the other hand, you have theism, and the idea here is that the order is upside down. Mind is at the bottom. The most fundamental stuff out there is not matter-like, but more like a mind. So it's not that somehow God just sort of turned up and magically learned all these things. God is simply it's being and truth itself, rather than something which has to sort of be formed out of stuff and then learn things. So it really is a difference in those basic worldviews that we're trying to think about tonight. So you shouldn't judge one by the other, is what I'm trying to say. You need to try to judge them on their own merits. So, for example, you think God is complex because God would have to have, great big, computer storage devices to remember all the stuff that everyone prayed for. Is not the right way to think about God. That's thinking in a materialistic way about what it would take to make a mind out of stuff, which is not the idea we're thinking about.
The second question is, are most cosmologists in agreement with the fine-tuning of the fundamental physical constants? And if so, are they more likely to grant the possibility of the existence of God than other scientists?
What I can really comment on is the scientific literature, and what I'd say there is most of the literature is, basically all of the literature is agreed to on the fine-tuning of, say, the cosmological constant. If you changed it, you wouldn't get life. And most of the literature is convinced of most of the other fine-tuning arguments as well. It's not totally unanimous, but it's there. It was there in the literature before anyone tried to do any kind of theology with it. It was just something weird noticed about the laws that we have. What this says sociologically about scientists or psychologically about what they believe about certain things is kind of hard for me to gauge. I'd guess that most cosmologists are probably atheists. I think so. For Geraint, my co-author, for example, he would say that the idea of God, he thinks, doesn't make a whole lot of sense, and so he believes that fine-tuning is telling us that there's a multiverse, for example. So you can try to understand determine which of those two is more likely. I should say on theism there could be a multiverse as well, but it's theism versus naturalism we want to think about.
So now there were a bunch of questions. So this is kind of two parts here. The first part is, does the fine-tuning of life in the universe, or fine tuning for the existence of life in the universe, make it likely that there is other life, other sentient life in the universe other than us? And if so, is that a problem for Christianity?
I don't think it says much about that. So, as a physicist, well, there's this thing called the Drake equation, which is trying to guess with equations how much life there is in the universe. So what you'd need to know is, all right, let's try and work it out. How many stars are there? How many planets are there attached to each star? How many of those what fraction of those planets will be in just the right place that life could exist? And then on what fraction of those will life actually come about? And in what fraction of those will life go on to be sort of intelligent like us? The problem is with that whole thing is we've got the astronomy done fine, so we're doing our bit. Number of stars, fine. Planets, about 1 per star. And we have a rough idea how many of them end up at the right distance from their star. And then it's the biology, because it's a much harder problem where we really don't know what's going on. So the question of is there life out there in the universe is totally open at the moment. And whether I don't think fine-tuning has much to say about that. If there was, the second part of the question was if there is life, is that a problem for theism? I don't think so. Someone told me the other day, actually, it was not just taught in the Middle Ages that it is possible that God made other life forms out in the universe, but it was heresy to teach otherwise. So you can read Thomas Chalmers at the start of the 1800s arguing against this kind of thing. That's ages ago, just saying that it's no assumption at all of Christianity that human beings are the only form of life in the universe. It's just not anything that we don't tell what God can do. So it is just neither here nor there. Unfortunately, distances are so long and our lives are so short, we'll probably never find out whether there is other life in the universe.
So now we have a couple of questions about the multiverse. The first question is, how widespread is it acceptance of the concept of a multiverse actually existing? And are there any other arguments against it other than the Boltzmann brain argument?
Let me give you this example. There's two very famous cosmologists, George Ellis and Joe Silk, one in South Africa and one in Oxford, who wrote an article fairly recently just totally trashing the multiverse, basically saying that this isn't science. So the argument against it is we're supposed to be scientists. What are we doing positing the existence of a huge number of completely unobservable entities that we'll never ever see? It's a pretty good argument, I've got to be honest. I think that kind of reason is why I think a lot of cosmologists are divided over this. I think Arent would say that the fine-tuning is strong enough that it's a big enough problem that we need to think seriously about the multiverse if you want a sort of scientific answer to this question. So I think it really has divided cosmologists. If you will find those who think that we need it to explain something and those who think that it is very obviously not science and is not the sort of thing that scientists should be dabbling in. So I think that answers the question.
So this question is asking basically why would we believe that an omnipotent being that exists want to create a universe such that we could exist in, such that moral beings could exist in?
Right, so at some point you have to ask that particular question if you're going to think through a fine-tuner. If there's just a powerful being out there, that's really not enough, right? Because you have all the possibilities, and power could make any of them, and that's all you can say about it. What really starts flipping down the possibilities is if you think that God is good, because then when we try to understand a person, we understand their motivations. And for a good being, we would want to see some moral value to the things that they do. That's a way of us trying to understand what's going on. So I think the argument I gave is fairly simple. We don't need to assume too much about morals of right and wrong. Just things like love is good. And so beings that can love are good, and God might want to do something which is good. And so one of the features of this argument, I think, is that however uncertain you are about that, you've got to weigh that off with the unlikeliness of getting a life-permitting universe on naturalism, which according to the sort of calculations, if they are, any indication of that number is ridiculously small, 1 in 10 to the 100 or something. So I don't think those sorts of worries about theism sway the balance too much. But, you know, you are going to have to think this through.
So this question is asking, how do we know that these constants aren't all related and maybe they're all just a function of one constant?
Sure, that's entirely possible. So maybe when we really understand what's going on, these constants couldn't have been otherwise. This is something that, this is actually the one bit in Chapter 8 that Geraint and I agree on, that would not actually answer the problem. What we want to do is look at a wide set of other possible universes to see what's going on, to see other ways the universe could have been. If it turns out that these constants could have been different, then we'll still want to do that sort of thing. But what we'll have to do now is, instead of taking the equation and changing the number in them, if we've actually got a higher equation with no free numbers in them, we'll just have to change the equation if we want to go and look through other possibilities. So actually, it just pushes the problem back a level. If you want to say why this particular mass of the electron versus all the other ones, you then ask a question, whatever that higher equation is, of why that equation rather than some other equation. Unless there's some sort of miraculous reversal of fortunes, it's likely that that sort of looking through other possibilities is going to give the same sorts of fine-tuning issues we see here.
Here we have two questions that are just physics questions. The first is, where is the center of the universe's expansion, and how do we know where that center is? The second is, if the universe is expanding and accelerating and light is constant, why can we still see the galaxies that are far away from us?
So, the idea of an expanding universe is that it's all expanding. So, we're trying to model here the whole of space itself. So we can't say that space itself is expanding into something, because the thing it's expanding into would itself be space. Here's the idea. Space itself is expanding, means that the distance between any two galaxies in space is getting bigger with time. So there's literally more space today than there was yesterday. Geraint likes to say that you could fit more oranges into the universe today than yesterday. So that's the model that we're going with. There's no center. So if you want a two-dimensional example, it's like the surface of the sphere. There's no center of the surface. The problem with this analogy is there's a center of the sphere, but we're trying to just think about the surface, okay? If you're on that surface and you're an ant and you didn't know anything about up and down, right? And it started expanding, everything else would be moving away from everywhere else on the surface of the sphere, but no ant would be in the center of the surface because it doesn't have one. That's the idea we have. That's the sort of thing you have to try and imagine if you're not going to say that space is expanding into space, which you can't say because it makes no sense. That's the idea of the expansion on Einstein's cosmology. Why can we still see things if expansion is accelerating? Is because they're close enough that the accelerated expansion of space hasn't completely put them beyond what's called the event horizon. We can predict when that will happen. It will happen in the future, but it hasn't happened yet, according to our best models of how this expansion has gone in the past. So we can still see the galaxies that are around us. For example, we're seeing, the Pinwheel galaxy might be it's probably a couple of million light years away. So in the total history of the universe, that's not too far away that we couldn't see it.
So the multiverse may not be scientific because it's not observable, but isn't God also unscientific because he's unobservable? So doesn't it at least put them on equal footing?
I think so. The multiverse and God could be this. Could both be true. So you don't want. It's not those two things which are against each other. It's it's theism, God, versus naturalism. That natural stuff is the only stuff. That's the way you need to think about this. So the question is, which one of those you think is more likely. So if you think the multiverse is not a scientific hypothesis and you're a naturalist, then you're in a bit of a problem because you can only accept scientific hypotheses and whilst remaining a naturalist. So if you think you need some explanation of the fine-tuning, then you're in a bit of trouble because you've wiped out a major candidate. God is not a scientific hypothesis. God is not made of stuff, right? God made the stuff. That's the whole point of it. It's not a scientific hypothesis because it's not a hypothesis about nature, about natural stuff, which is what scientific hypotheses are about. It can, we can still think about it and we can still understand it. And if we want an explanation for questions like why is there natural stuff at all, we are going to have to get used to there being explanations which are not in terms of natural stuff. So I don't think that's a good way to criticize the idea that there's a God. It might be wrong, but the fact that it's not scientific is just the nature of the case. If you want to start with the assumption that the only true hypotheses are scientific hypotheses, you've just assumed naturalism from the start, so you haven't really proved anything.
This questioner asks, your presentation points to a creator. How does that translate to a personal God, Christianity as the true religion?
So, at worst, all it does is says that there's some good creator of the universe, and then if you want to know more, you're going to have to get information from somewhere else, right? At worst, that's what it shows, right? So if you're a Christian, it shouldn't come as that much of a surprise. You might have to read the Bible to work out Christianity, right? Shouldn't be like a massive problem. I think there are ways in which this fine-tuning fits in better with Christianity than with some other religions, maybe. The doctrine of the Trinity puts a sort of love and relationship at the very heart of what God is, as opposed to perhaps in other religions where love is just an attitude that God happens to have. That might give Christianity an advantage, but I mean, there's only so much you can prove from an argument like this, so I'm quite happy to say it might bring you to theism, and there's a good creator God who could, if they like, do miracles or those sorts of things. And if you have that as a possibility in mind when you, say, read the New Testament, it's going to read very differently from if you think that's all nonsense and not even possible.
From Twitter, we have a technical question. The questioner says, you mentioned the Planck cutoff because we don't know what happens after that. What if the numbers go off to infinity? Doesn't fine-tuning become meaningless?
If there's an infinite range of these numbers, and that stops us from saying how likely is it that life would come about. So the point is, if you try to do a probability, so you say, here's the range that gives life, so the probability of life is roughly that size over that size, okay? This is sort of the rough thing you want to do to get a probability. If the total size is infinite, it seems like you haven't got an answer to that question at all. The problem with that response, I would say, is that if you want to take your scientific theory and predict what would we expect to see, if these infinities cause a problem for you, they cause a problem for you predicting anything, not just the probability of life. So what you've found is not a reason to doubt fine-tuning for life, but just to doubt that your theory can predict anything. Now, these are theories which clearly we think can predict something because they are currently the best theories we have about the universe. Okay? So it's up to, I would say, slightly technical, but it's up to the theory to tell us what values of the parameters are likely and to sort out which ones are probable and to give us the range of values. So if we've got a theory that's doing all of that, it will be able to be tested, and then we can use it to ask questions about how could things have been different.
Now we have a couple of questions about the Big Bang. What triggered the Big Bang, and what existed before the Big Bang?
Just quickly, there's need to have a distinction in mind when we talk about the Big Bang. There is something called the Big Bang theory, which just says that in the past the universe was more dense and hotter, and that's all it says. It's a statement about, the universe is expanding, so in the past it was denser and hotter, and if we follow that idea, we would expect certain things to be true about the universe, which turn out to be roughly true. That's the Big Bang theory. There is also the Big Bang. If you wind the clock back on this theory, in just a standard Einstein theory of gravity, you arrive at a beginning point, okay, which we call the Big Bang. But that's winding the theory past the point where we've got no evidence about whether it's correct or not. We can test it sort of later on in the universe, closer to today, obviously. But in the very earliest stages, we both run out of evidence, and then we run out of theory because our theories don't really tell us what happened. So that's the Big Bang itself. So the question, what triggered the Big Bang, depends on whether you're taking that point seriously. If you think it's a boundary of space-time, then there's nothing physical other than space-time, and so nothing physical triggered the Big Bang, and nothing came before it, because it's the beginning of space and time, and you can't come before time, right? So that raises all sorts of interesting questions. If you think that that's a beginning, and you think that universes don't just pop into existence for no reason whatsoever, that's another reason you might have to think that there is a creator. It's called the Kalam cosmological argument. Just to say it's a different argument to this one. It depends on how much you think the data we have is pointing to a beginning. So that's another talk for another day.
We have another question from Twitter. Star Wars or Star Trek?
For me, Star Wars. For Geraint, Star Trek. If you read the book, you will see that played out again and again. Every Star Trek reference is his. Every Star Wars reference is mine.
How do you think that the concept of time plays into the beginning of the universe and potentially the creation story in Genesis?
So there's two things there. How time relates to the beginning is what I said there. If there's a Big Bang that's a boundary of space-time, then it is simply a beginning. You can't have something before time. It's not just, it would be the beginning of time itself. How you read Genesis is a massive question that will not be sorted out by me in the next 30 seconds. You're going to need to read it and have a very hard think about it yourselves. If you want to ask me more about that, feel free to come up. I have my own opinions on it, and so does everyone else.
Okay, this is our second to last question. When you talk about life, are you talking about a physical phenomenon or a non-physical phenomenon?
Oh, just a physical phenomenon. So, in this sense, when you're thinking about what God might want to create, if you're sort of thinking through that idea, morals, a morally valuable thing would be able to give love and receive love. So there must be some way that finite beings can interact with each other. There must be something called me and something called you, and a common space between us that we can both manipulate but not totally control. That I would call, sort of by definition, the physical universe. So that's the way they would sort of fit into that scheme of things. But I'm entirely thinking of a physical phenomenon.
So our last question here is, what do you think of the position of simply not caring about the reason why the cosmos is the way it is? And then, do you believe in a fine-tuner?
Yes, I do. To answer the second one. Why not just not care? You're just as... It's just as easy to be wrong by not following the evidence to a conclusion, as in sort of refusing to follow the evidence, as in to be wrong by following evidence the wrong way. It's not true that the person who doesn't believe something always has the advantage, right? If I was in Dallas the other day looking at the JFK Museum, right? If you look at the evidence for what happened, it's all laid out there. Nice, it's really quite fantastic, right? You're just as likely to be wrong by simply refusing to believe the evidence that's there as you are by choosing one particular theory over another one. So if we want to, if you don't care about whether what you believe is true, then feel free not to care about this sort of thing. But if you want to know whether your ideas are true, you're going to need to think about the kind of thing that makes a good explanation about what we have learned about the universe around us and about what we would expect to see if certain ideas were right. If naturalism were true or if theism were true, what would we expect to see? And you need to think through all of those ideas. And you are just as likely to be wrong by refusing to follow evidence that is there than as following evidence to the wrong conclusion. So I don't think there's sort of a neutral standpoint here. I like the joke that agnostics should go to church every second Sunday just to hedge their bets a bit, right? You need to. You'll make a decision in your life one way or the other. You might as well make it based on the evidence and on truth.
Let's thank Dr. Barnes again for being here tonight.